In this example, we're asked to look at the free response of the single degree of freedom system that's shown. We got a particle of mass m. We have three springs, each of stiffness k. Between that particle and ground, we have a dashpot of damping coefficient c between the block and ground. And we're describing the position of the particle in terms of the variable of x, where x is measured positively to the right. We're given m, c, and k. We're given the initial conditions. Find the response. So the first thing we need to do, of course, is to derive our equation of motion. Kinetic energy T, 1/2 mv squared, so that's x dot squared. The potential, 1/2 kx squared for each one of the three springs. There are three of them. And then the Rayleigh dissipation function, which is equal to 1/2 cx dot squared. And since there are no forces that do non-conservative work that we're not already putting in u and r, then dw is a 0. So from this, our equation of motion is mx double dot plus cx dot plus 3k x is 0. That is our equation of motion. What I'm going to do is divide the equation of motion through by the leading coefficient in the equation. So I'm going to divide through by n, whatever is appearing in front of x double dot. So this gives me x double dot plus c over m, x dot plus k over m x is equal to a 0. So we know that this is, from what we've seen in class, what we define to be omega n squared. This is what we would define to be 2 zeta omega n. Therefore, omega n is equal to the square root of 3k over n. So that's the square root of 3. K was given to us to be 2,500. The mass is 3 kilograms. So we have a natural frequency, undamped natural frequency of 50 radians per second. We know that 2 zeta omega n, that was defined to be c over m. So from that we have the damping ratio to be c divided by 2 m omega n. C is 9. 2, the mass again is, what did we say, 3. We found omega n was 50. And so the damping ratio ends up being 0.03. The damped natural frequency, omega n, times the square root of 1 minus zeta squared. So that's equal to 50 times the square root of 0.991. Effectively is the same thing as omega n. Effectively, it's 50. The important thing here is that since we found that the damping ratio is less than 1, the form of the free vibration response is our damped harmonic. So this is x of t is e minus zeta omega nt, a cosine omega dt, plus b sine omega dt. Like this. We enforce our initial conditions, so x at time equal to a 0 is a 1 for the exponential, a times 1 plus b times a 0. So from this we see that a is equal to the initial value of x, which is equal to 0.1. The time derivative of x is minus zeta omega n E minus zeta omega nt, A cosine omega dt, plus B sine omega dt, plus an E minus zeta omega nt, minus A omega d sine omega dt. All I'm doing is doing a time derivative of the expression there for x. We have a lot of terms here because the product rule is involved. So from this, we see that the initial value for x dot, which is given to be a 2, on the right-hand side, we simply have a minus zeta omega in A. We have an omega d times B. So from this, we have that B is equal to 2 plus zeta, which we just found, omega n, times A, which we just found, omega d we just found. So we now know B. So that's it. The problem here came down to first getting the equation of motion. We for sure needed to know the numerical values for the damping ratio and frequencies, but importantly, we needed to know the qualitative nature of the response, and that depends on the size of the damping ratio. Damping ratio was less than 1, so we had damped harmonics for the response. We enforced our initial conditions to get those two coefficients.